Equilibria labeled polytopes. To identify the possible supports of equilibrium strategies, one can use best response polytopes that express directly the inequalities of best responses and non-negative probabilities. We first recall some notions from the theory of convex polyhedra. An affine combination of points z1, z2, z3 until zk in some Euclidean space is of the form the summations of zi times lambda I summing with index I starting from 1 to k, where lambda 1, lambda 2 until lambda k are reals, with the summations of lambda I summing with index I starting from 1 to k equals to 1. It is called a convex combination if lambda I is greater than or equals to 0 for all I. A set of points is convex if it is closed under forming convex combinations. Given points are affinely independent if none of these points are an affine combination of the others. The convex set has dimension d if and only if it has d plus 1, but no more affinely independent points. A polyhedron P in R to the D is a set Z in RD such that C times Z, which is less than or equals to Q for some matrix C and vector Q. It is called a full dimensional if it has dimension D. It is called a polytope if it is bounded. A face of P is a set Z in P such that C transpose times Z equals to Q0 for some C in R to the D and Q0 in R, so that the inequality C transpose times Z is less than or equals to Q0 holds for all Z in P. A vertex of P is the unique element of a zero-dimensional face of P. An edge of P is a one-dimensional face of P. A facet of a d-dimensional polyhedron P is a face of dimension d minus 1. It can be shown that any non-empty face f of P can be obtained by turning some of the inequalities defining P into equalities, which are then called binding inequalities. That is, f equals to the set Z in P such that Ci times Z equals to Qi for all those little I in capital I, where Ci times Z is less than or equals to Qi for little I in capital I, are some of the rows in Cz less than or equals to Q. A facet is characterized by a single binding inequality which is irredundant, i.e., the inequality cannot be omitted without changing the polyhedron. A d-dimensional polyhedron P is called simple if no point belongs to more than d facets of P, which is true if there are no special dependencies between the facet defining inequalities. The best response polyhedron of a player is the set of that player's mixed strategies together with the upper envelope of expected payoffs and any larger payoffs to the other player. For player 2 in the example 3.3, it is the set Q bar of tuples, of triples y4, y5u that fulfill 3y4 plus 3y5 is less than or equals to u, 2y4 plus 5y5 is less than or equals to u, 0y4 plus 6y5 is less than or equals to u, and y4 which is greater than or equals to 0, y5 is greater than or equals to 0, and y4 plus y5 equals to 1. The first three inequalities in a matrix notation a y less than or equals to 1 times u say that u is at least as large as the expected payoff for each pure strategy of player 1. The other constraints y, which is greater than or equals to 0, and the one vector transpose times y equals to 1 state that y is a vector of probabilities. The best response polyhedron P bar for player 1 is defined analogously. Generally, P bar equals to the set of xv in R to the n times R, such that x is greater than or equals to 0, 1 transpose times x equals to 1, v transpose times x is less than or equals to 1 times v, and q bar is equals to the set of yu in R to the n times R, such that ay is less than or equals to 1 vector times u, y is greater than or equals to 0, and the transpose of one vector times y is equals to 1. The left picture in figure 3.1 shows q bar for our example for 0 less than or equals to y4 less than or equals to 1, which uniquely determines y5 as 1 minus y4. The circled numbers indicate the facets of q bar, which are either the strategies I in n of the other player 1 or the own strategies j in n facets 1 to 3 of player 1 indicate his best responses together with his expected payoff u. For example, 1 is a best response when y4 is greater than or equals to 2/3. Facets 4 and 5 of player 2 tell when the respective own strategy has probability 0, namely y4 equals to 0 or y5 equals to 0. We say a point yu of q bar has label k in M union n if the kth inequality in the definition of q bar is binding, which for k equals to 1 in M is the ith binding inequality. The summations of ai j times yj, summing for all those j in n equals to u, meaning I is a best response to y. Or k equals to j in n, the binding inequality yj equals to 0. In the example y4, y5, u equals to 2/3, 1/3, 3 has labels 1 and 2, so rows 1 and 2 are best responses to y with expected payoff 3 to player 1. The labels of a point xv of p bar are defined correspondingly. It has label I in M if xi equals to 0, and the label j in n if the summations of bij times xi summing for all those index I in M equals to v. With these labels, an equilibrium is a pair xy of mixed strategies, so that with the corresponding expected payoffs v and u, the pair xv-yu in p bar cross product q bar is completely labeled, which means that every label k in M union n appears as a label either of xv or of yu. This is equivalent to the best response condition 3.2. A missing label would mean a pure strategy of a player, e.g. I of player 1, that does not have probability 0, so xi is greater than 0 and is also not a best response, since the summations of aij times yj summing for all those index j in n is less than u, because the respective inequality I is not binding in a p bar or q bar, but This is exactly when the best response condition is violated. Conversely, if every label appears in P-bar or Q-bar, then each pure strategy is a best response or has probability 0, so X and Y are mutual best responses. The constraints 3.4 that define P-bar and Q-bar can be simplified by eliminating the payoff variables U and V, which works if these are always positive. For the purpose, assume that A and B transpose are non-negative and have no zero column. We could simply assume that A is greater than 0 and B is greater than 0, but it is useful to admit zero matrix entries, e.g. as in the identity matrix. Even negative entries are possible as long as the upper envelope remains positive, e.g. for A34 or A31, currently 0, in 3.3 as figure 3.1 shows. For P-bar, we divide each inequality. The summations of Bij times Xi summing for all those index I in M is less than equals to V by V, which gives the summations of Bij times Xi over V summing for all those I in M, which is less than equals to 1. Treat Xi over V as a new variable that we call again Xi and call the resulting polyhedron P. Similarly, Q bar is replaced by Q by dividing each inequality in AY less than equals to 1 times U by U. Then P equals to the set of X in R to the N such that X is greater than equals to the 0 vector and B transpose times X is less than equals to the 1 vector. Q is defined as the set of Y in R to the N such that AY is less than equals to 1 and Y is greater than equals to 0. It is easy to see that 3.5 implies that P and Q are full-dimensional polytopes, unlike P bar and Q bar. In effect, we have normalized the expected payoffs to be 1 and dropped the conditions 1 transpose times X equals to 1 and 1 transpose times Y equals to 1. Non-zero vectors X in P and Y in Q are multiplied by V equals to 1 over the 1 vector transpose times X and U equals to 1 over the 1 vector transpose times U to turn them into probability vectors. The scaling vectors V and U are the expected payoffs to the other player. The set P bar is in 1-to-1 correspondence with the P minus 0 vector, the set of the 0 vector with the map X V maps to X dot 1 over V. Similarly, Y U is mapped to Y dot 1 over U defines a bijection Q bar to Q minus the 0 vector. These bijections are not linear, but as known as projective transformations. For visualization, see von Stengel 2002, figure 2.5. They preserve the phase incidences since abiding inequality in P bar respectively Q bar corresponds to abiding inequality in P respectively Q and vice versa. In particular, points have the same labels defined by the abiding inequalities, which are some of the m plus n inequalities defining P and Q in 3.6. An equilibrium is then a completely labeled pair xy in P times Q minus the set of the pair 0 vector, 0 vector, which has for each label I in M the respective binding inequality in X which is greater than or equals to the 0 vector, or AY is less than or equals to the 1 vector, and for each J in N the respective binding inequality in the B transpose times X is less than or equals to the 1 vector, or Y is greater than or equals to the 0 vector. For the example 3.3, the polytope Q is shown on the right in figure 3.1 and in figure 3.2. The vertices Y of Q, written as Y transpose, are 0, 0 with labels 4, 5, vertex P equals to 0, 1, 6 with labels 3, 4, vertex Q equals to 1, 12, 1, 6 with the labels 2, 3, vertex R equals to 1, 6, 1, 9 with labels 1, 2, and S equals to 1/3, 0 with labels 1, 5. The polytope P is shown on the left in figure 3.2. Its vertices X are 0 with labels 1 to 3. And written as X transpose vertex A equals to 1/3, 0, 0 with labels 2, 3, 4. Vertex B, which is equals to 2, 7th, 1, 14th, 0 with labels 3, 4, 5. Vertex C equals to 0, 1, 6th, 0 with labels 1, 3, 5. Vertex D equals to 0, 1, 8th, 1, 4th with labels 1, 4, 5. And E equals to 0, 0, 1/3 with labels 1, 2, 4. Note that the vectors alone show only the on labels as the played on strategies. The information about the other players' best responses is important as well. The following three completely labeled vertex pairs define the Nash equilibria of the game, which we already found earlier: the pure strategy equilibrium AS and the mixed equilibrium BR and DQ. The vertices C and E of P and P of Q are not part of an equilibrium. Non-degeneracy of a bimetric game AB can be stated in terms of the polytopes P and Q in 3.6 as follows. No point in P has more than M labels, and no point in Q has more than N labels. If X in P and X has support of size K, and L is the set of labels of X, then the size of L intersects M equals to M minus K. So the size of L is greater than M, implies X has more than K best responses in L intersect N. Then P and Q are simple polytopes because a point of P, say, that is more than M facets, would have more than M labels. Even if P and Q are simple polytopes, the game can be degenerate if the description of a polytope is redundant, in the sense that some inequality can be omitted, but nonetheless is something binding. This occurs if a player has a pure strategy that is weakly dominated by or payoff equivalent to some other mixed strategy. Non-simple polytopes or redundant inequalities of this kind do not occur for generic payoffs. This illustrates the assumption of non-degeneracy. From a geometric viewpoint, a strictly dominated strategy may occur generically, but it defines a redundant inequality that is never binding. So this does not lead to a degenerate game. Because the game is non-degenerate, only vertices of P can have M labels, and only vertices of Q can have N labels. Otherwise, a point of P with M labels that is not a vertex would be on a higher dimensional face, and the vertex of that face, which is a vertex of P, would have additional labels. Consequently, only vertices of P and Q have to be inspected as possible equilibrium strategies. Algorithm 3.5 Equilibria by vertex enumeration. Input: a non-degenerate bi-matrix game. Output: all Nash equilibria of the game method for each vertex x of P minus the set of zero vector, and each vertex y of Q minus the set of zero vector. If xy is completely labeled, output the Nash equilibrium x dot 1 over the transpose of one vector times x, and 1 dot 1 over the transpose of one vector times y. Algorithm 3.5 is superior to the supported enumeration algorithm 3.4 because there are more supports than vertices. For example, if m equals to n, then approximately 4 to the n possible support pairs have to be tested, but p and q have less than 2.6 to the n many vertices by the upper bound theorem for polytopes. This entails less work, assuming that complementary vertex pairs xy are found efficiently. Enumerating all vertices of a polytope P, say, is a standard problem in a computational geometry. The elegant LRS lexicographic reverse search algorithm considers a non-vertex like zero vertex for P in 3.6 and a linear objective function that over P is maximizes at the vertex like the function x, which maps to -1 transpose times x, -1 vector transpose times x. For any vertex of P, the simplex algorithm with a unique pivoting rule, e.g. blend least index rule for choosing the entering and the leaving variable, then generates a unique path to 0. Defining a directed tree on the vertices of P with root 0, the algorithm explores that tree by a depth-first search from 0, which reverts the simplex steps by considering recursively for each vertex x of P the edges to vertices x prime so that the simplex algorithm pivots from x prime to x.